But what I wanted to start off with today is applying Neville's method to a probability and statistics application. We're going to apply Neville's method and also a new method with regard to these divided differences that I just mentioned to interpolating what it'll be the CDF, cumulative distribution function of the standard normal distribution. Why am I picking this application? Well, for one thing, it's an important application to statistics, right? Standard normal distribution, very important in statistics. And for another thing, the CDF, cumulative distribution function of the standard normal distribution function, is a non-elementary function. It cannot be expressed in terms of exponentials, trig functions, logarithms, polynomials in exact form with finitely many terms or finitely many compositions. It's a non-elementary function. So that's some more significant reason to have interpolation methods, you might say, even nowadays with computing technology. Certainly Mathematica and calculators can handle it, but it could conceivably be something you might have to program in, R or Python on the job or something like that for some reason if you got some sort of other applications that are going on in R or Python, for example. So what is the CDF? Well, first of all, what's the PDF? The PDF of the standard normal distribution, N0, 1, meaning 0 is the mean, mu, and 1 is the variance, sigma squared, which is also the same as the standard deviation, since the square root of 1 is 1. We know it's your classic bell-shaped curve centered at 0. Standard deviation of 1. The standard deviation does happen to measure the horizontal distance between the vertical line of symmetry and the inflection points on either side. So -1 and 1 are inflection points for the standard normal distribution. And what is the formula for this PDF, this probability density function? Its formula is 1 over square root of 2 pi e to the negative x squared over 2 power. We're going to use both Mathematica and spreadsheets today. Oh, where's my Mathematica here? There we go. Let's confirm that that's the right PDF. PDF normal distribution 0, 1. Mathematica's syntax is to put the standard deviation there in that second spot. We know in prob and stats, we typically put the variance there. Comma x. There it is. Yeah, e to the negative x squared over 2, all divided by square root of 2 pi. That is the probability density function, modeling the fact that when you've got data modeled by a standard normal distribution, the data are denser where the graph is higher, so that denser close to 0 and less dense far away from 0. You'd have outliers far away from 0. To be a PDF, we know it's got to be non-negative, which it is. We know its integral over the entire real number line, which is an improper integral, has to equal 1, which is why you end up dividing by square root of 2 pi. And by the way, I did notice I still have to watch this on 3 blue, 1 brown. There's recently some videos about normal distributions and the central limit theorem, I believe. And it's addressed why pi is in this formula from an intuitive standpoint. I haven't watched it yet, but I need to. What's the CDF? The CDF, capital F of x, as always, is going to be the integral of the PDF. Technically from minus infinity up to an arbitrary value of x, f of t dt. The t here is just a dummy variable. It doesn't really mean anything. I'm just trying to use something different than x in there. Maybe you'd prefer using u or z or something. That's the CDF of a standard normal distribution. What is its formula? Well, I already mentioned that it's a non-elementary function. What does Mathematica say its formula is? What's the CDF? ERFC. Okay, it's a non-elementary function. What does ERF stand for? It stands for error function. Why do they call it an error function? It's because it's related to experimental errors. What's the C stand for? I think that means complementary error function. Actually, this is not the unique way to write it, but if we do plot this graph, we get a graph that does look like a typical CDF. Goes to 0 as x goes to minus infinity. Actually, the graph looks like it goes below 0, but that is not correct. A little bit inaccurate looking there. And then goes to 1 as x goes to plus infinity. And do notice that capital F of 0 is 0.5 as it should be. The area under the standard normal curve to the left of 0 would be 0.5. What else could you say about this thing? If you plug in, for example, 1 in place of x, that's representing a z-score. Well, 1 is a z-score for the 84th percentile. Some people memorize that. Other special numbers that people often memorize is if the z-score is 1.282, I think. That's pretty close to the 90th percentile. 1.645 is pretty close to the 95th percentile. Probably your favorite one, 1.96 is close to the 97.5th percentile, corresponding to the number you use as a multiplier for the margin of error for a 95% confidence interval. And another fairly famous one, I believe, is I think it's 2.576, 99.5th percentile, corresponding to the multiplier of the margin of error of a 99% confidence interval. Let's use those numbers as data for interpolation. So f of 1, capital F of 1, is pretty close to 0.84. Okay, let's go ahead and use more decimal places. 0.841345. These are going to be our nodes that we're going to use for interpolation here. Capital F of 1.282, let's see what that is. Again, 1.282, pretty close to 0.9. 0.9000079. Going to have 4 nodes. 0th node, 1st node, 2nd node, 3rd node. 2 more here. 1.645, pretty close to 0.95. 0.950015. And let's use 1.96 as our last one. Well, actually, let's go up to the 2.576. F of 2.576 is about 0.995002. And let's now try to use these data. Excuse me. Goal is to approximate capital F of 1.96. We know what the answer should be. Close to 0.975. 1.96, close to 0.975. Let's see how interpolation does. It's 4 data points, 4 nodes. X0 is 1. X1 is 1.282. X2 would be 1.645. X3 would be 2.576, right? Is there a question?
How do we know what it's supposed to be?
I use Mathematica.
Oh, okay.
That's X3, 4 nodes, starting with the 0th node. If we're doing a polynomial interpolation, It's really going to be a cubic. And again, we could approach it as we did originally, solve a system of linear equations. They would be 4 equations and 4 unknowns. Certainly Mathematica could do it, but let's get some practice again with Neville's method by hand with calculator help this time. So we did it in a spreadsheet last time. Let's think about how to construct the table. This is not going to be as high a degree as we did in the spreadsheet. We did a 5th degree in the spreadsheet. This here, we're just doing a 3rd degree, so it's not quite as bad. This will be good to review. So we've got the subscript numbers, 4 of them starting with 0, 0, 1, 2, and 3. We've got the xi's themselves, the nodes. 0th node is 1. First node is 1.282. Second node, which is 1.645. Third node, which is really the 4th node, is 2.576. X minus xi was the next column. Not sure if I'm making these small enough. I'm going to run out of room on my paper. Let's see what happens here. X, what is X? X is 1.96. That's going to be our X. So we'll go ahead and start using the calculator now. Well, we don't really need to for this. This one, okay, 1.96 minus 1 is 0.96. 1.96 minus 1.282 is 0.678. 1.96 minus 1.645 is 0.315. Putting the zeros in front, I won't bother with that in the future here after this next one here. 1.96 minus 2.576 is negative 0.616. All right, remember what comes next. It's the TIs, which are function values. These are essentially 0th degree polynomials approximations, which are constant functions. It's just the y values. It's just these numbers that I already have. It's the data. In terms of the Q notation, it's, let's see. That's the first column, 0th column, but different rows. I think it would be row I, column 0. We start the labeling with zeros. Just the data. Again, this would be 0.841345. Looking up at the numbers up here. Then 0.900079, 0.950015, and 0.995002. Those are easy. Just the outputs of the function that we're given. Next question.
Label that column 0th degree and like 1st degree. Like, is it the same thing to say that?
Yeah, you could put the 0th degree if up here if you want.
Okay.
Next column is going to be for the 1st degree approximations, linear functions. Labeled P sub I, comma, I plus 1. 2 subscripts to emphasize we're using 2 nodes. For example, the 0th row, we'd be using the 0th node and the 1st node. In the 1st row, we'd be using the 1st and 2nd nodes. In terms of the Q notation, once again, the row of the Q is the I, the 1st subscript there, and the column is now the 1st column. Now we have to start doing calculations. For the 1st degree column, we start with a number that goes in this spot. And what is this number about? The number that goes here is going to be from a linear interpolation of the data for the 0th and 1st nodes, when xi is 1 and 1.282, and the function values are 0.841345 and 0.930000079. I'm effectively connecting those points with a straight line and going out further to the right to get an approximation to the function at x equals 1.96 further to the right. Question?
So there's the reason of that first, like right above that is blank is because if you did like try to connect two dots on top of each other, it just wouldn't be useful.
No, it's just a convenience. It would be better to put it like halfway between the 0 and 1 to emphasize I'm using those two, but in a spreadsheet, you've got to put it either right there or right there. So by convenience, we just put it there. That's why. On a table by hand, we could put it sort of like halfway between. Okay. So the method is to take this number times this number, the numbers upper left to lower right, subtract this number times this number, and then divide by this number minus this number. So let's go ahead and do those details. 0.96 times 0.9000079, upper left to lower right product, minus 0.678 times 0.841345, lower left to upper right, divided by the difference, 1.282 minus 1, divided by 0.282. 1.041290.5. Let's write that down. Like that. Now remember, when we did this on a spreadsheet last week, this formula was then copy and pastable downward, meaning I do the exact same things, but shifted downward by one row. So for this next number, I'm going to do the product of this times this minus the product of this times this divided by the difference, this minus this. Okay. I think earlier I did the wrong difference in the bottom. That was maybe what the problem was. So 0.678 times 0.950015, product of those two, minus 0.315 times 0.9000079, divided by, use parentheses, 1.645 minus 1.282. 0.9933, that, and it is a bit too big. That's what I was expecting. 0.9933479. One more to do. Copy and paste the formula downward. So we do this times this. Then this time minus this times this. All divided by this minus this. This should be the closest answer. So 0.315 times 0.995002 minus, careful, actually, well, because that's a negative sign. Subtracting a negative is the same as adding, so I'll do an adding here. 0.616 times 0.950015. Divide by the difference, 2.576 minus 1.645, and I'm afraid I'm going to get the wrong answer here. Oh, okay, that's better. That's better. That one is the closest, and it's, to me, it's not surprising that it's maybe a little too low because now we are using a node that's to the right of 1.96. 0.965236. The next column, you're using second degree polynomials, quadratics. Subscript labeling P sub I plus 1, I plus 2 equals Q sub I comma 2. This labeling emphasizes using 3 nodes. This labeling emphasizing the row and the column. The row corresponding to the value of I. Second column really meaning third because we start 0th column, first column, second column. Degree of the polynomial is the second subscript for the cube. We start with this one though, and this is where it does get a little extra tricky. Because now, in this column, we do need to go back to using that number there and this number here, but not this number in between. Which seems a little weird. Shouldn't you still have to use the data in between? And the answer is, I haven't shown you the details of the algebra, but it ends up being that you are using it without realizing, in a sense, because you're using it with this number here ultimately. So you do 0.96 times this number. I think this will be the last time I make this kind of picture here because it's getting so messy. Minus 0.315 times this number. So on this column here, the numbers are right next to each other, but in this one here, they're 2 apart. All divided by this number minus this number, 1.645 minus 1. We're almost done. We're getting close, right? We just got a few more to do here. So 0.96 times 0.9933479. Remember, we should expect a final answer pretty close to 0.975 by this point. Minus 0.315 times 1.0412905, all divided by 1.645 minus 1, meaning divide by 0.645. 0.9699. 341. We copy and paste that formula downwards, so we need to use 0.678 now times this number, 0.9652362. Product of those two minus the product of these two. That's got a negative sign, so I'm really going to add 0.616 times 0.9933479. And then divide by 2.576 minus 1.282. 978,618.6. Just one more thing to calculate. That will be our third degree, because we have 4 nodes. P sub I, comma I plus 1, comma I plus 2, comma I plus 3 equals Q sub I, comma 3. It is a third degree. I won't draw the numbers anymore with the lines. Go back to the x minus x0, 0.96 times that, minus this times that, divided by 2.576 minus 1. 0.96 times 0.9786186 minus the product of these two. That's got a negative sign, so I'll do a plus. 0.616 times 0.9699341 divided by 2.576 minus 1 means divide by 1.576. All right, we're close to 0.975. 975,224 to say as our final third degree approximation to capital F of 1.96. That's a lot to do, isn't it? Check it again, compare it. It's in reality 0.975002. So what's the error? The error would be the actual value minus this approximation, a negative error close to negative 0.0002 with the third degree polynomial approximation. Seems like a lot of work, and it is certainly by hand, even with calculator help. Something you can do fairly quickly. We saw last week in a spreadsheet. Probably better something you could program in a programming language like Python or something that could make it more automatic. But of course, you've already got built-in things like Mathematica, built-in functions, calculator, and on a calculator, we could compute this like this. We could go to the normal CDF and do a 1.96 here. Mu is 0, sigma is 1, paste. Yeah, there's our 0.975002. Okay. So you, in a sense, really don't need to do these things, but it's, it's good to know about them in case you ever do some programming to realize these methods are out there. It's still a worthwhile thing to look at. And the other video, it's a worthwhile thing to understand as well, that you're using these polynomial approximations. For our final 27 minutes or so, we're going to consider the same problem. We're still approximating the CDF of a standard normal distribution based on these data. F of 1 is 0.841345. F of 1.282 is 0.90079. F of 1.645 is 0.950015, and F of 2.576 is 0.995002. And we're going to approximate once again. Goal. That's the bad pen. Approximate. Estimate. That one's bad too. F of 1.96. But now we're going to use a different method. Still best to use a spreadsheet for this method. But once again, today, we're doing it by hand. Maybe we'll have time for the spreadsheet, but I'm not sure. It's divided differences method. Hands are just not working so well today. Divided differences method. Divided differences. It's somewhat similar to Neville's method, but definitely different. Pun intended. Bad pun. With Neville's method, okay, here's the main difference conceptually. With Neville's method, we were really computing values of a bunch of different interpolating polynomials. The 0th column, we had, with the example we just did, we had 4 p's. We had 4 constant polynomials. Then with the 1st degree column, we had 3 linear polynomials. With the 2nd degree column, we had 2 quadratic polynomials. And with the 3rd degree column, we had 1 cubic polynomial approximation to the function value at 1.96. You didn't actually have to compute the polynomials themselves at all. With divided differences method, we're actually computing the polynomial in a sense. We're computing the coefficients of the polynomial, and we're going to use the formula for the polynomial based on these coefficients. But the polynomial is not written in standard form. The polynomial is written kind of a strange form. A constant, call it A0, plus another constant, call it A1, times x minus the 0th node, plus another constant, call it A2, times x minus the 0th node times x minus the 1st node, etc. Remember, in general, you got n plus 1 points, n plus 1 nodes, starting with the 0th node and going through the nth node. So you need an nth degree polynomial. The last coefficient label would be a sub n times x minus x0 times x minus x1 times dot, 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 times, careful here, it's x minus x sub n minus 1 instead of x sub n. Think about it here. This has got to be an nth degree polynomial. We start our node labeling with 0th node. There are n factors here when this last subscript is n minus 1. That's going to make this an nth degree polynomial. Not written in standard form, right? This is not a standard form for a polynomial. Not written in factored form. Written in this way, this kind of weird way you've probably never really seen before. It turns out then, through some very complicated algebra, well, the first step is not very complicated algebra. A0 does happen to equal the function value at the 0th node. That's easy to see. If you replace x with x0, the 0th node, for all these other terms, they go away, right? They're all 0. That's f of x0. In this section, we're also going to write that with square brackets as if it's Mathematica, but it's not a Mathematica thing here. This is called a 0th divided difference. And you then ask yourself, well, where is the division and where is the difference? Well, there is no division and there is no difference. That only comes up once you get to the first divided difference and the second divided difference and the third divided difference. The 0th is kind of a special case. A1 is not a function value, though it's related to function values. It's a first divided difference, and the notation is to use square brackets again with x0 and x1. This is a first divided difference. I'll just call it first DD. And it really is a division of differences. Thus, the name divided difference. It's f of x1 minus f of x0 divided by x1 minus x0. Hey, it looks kind of like a difference quotient from calculus. Should we take a limit of it? No. No calculus here. In calculus, it's funny. We call this a difference quotient, a quotient of differences. Here we call it a divided difference, a division of differences, right? Quotient is synonymous to division. Okay. It turns out that's what A1 equals. Through slightly complicated algebra. You can solve for A1. Because you can solve for all these A's by plugging in the different nodes. X0 easily makes you solve for A0. Plug in X1 as well. All these other terms go away because they all have X minus X1s in them. This term doesn't go away. You can solve for A1 in terms of A0, which is f of X0. They're the same as A0. It's not too hard to solve for A1. With the next one and those after it, the algebra solving is pretty nasty. At least writing them in the form I'm going to show you. It turns out that A2 is, well, we've had a 0th divided difference and a first divided difference. How about a second divided difference? F of x0, x1, x2. A second DD. It's iterative. It's a divided difference of first divided differences. It's f of, okay, this is a little tricky because I'm going to write down some things that are not yet defined. F of x1 comma x2 minus f of x0 comma x1 divided by x2 minus x0, where this term comes from this one. But where does this one come from? We haven't actually written it down, but it's analogous to this one. F of x1 comma x2 is f of x2 minus f of x1 divided by x2 minus x1. So you are going to actually have to compute that divided difference as well. This is a first divided difference. I just didn't write it down before this point. It's not equal to A1, but it's necessary in computing A2. Again, the algebra to verify that this works is way nastier than you might imagine. And the extra video that's optional for you to watch, I actually show the algebra. It's way nastier than you would imagine. It's surprising, actually, that this works. We keep iterating. A3 is going to be a third divided difference that's going to have 4 nodes inside the square brackets, x0, x1, x2, and x3. This is a third DD. Oops. Third DD. And again, it's iterative. It's a divided difference of second divided differences. Which ones? F of x1 comma x2 comma x3 minus f of x0 comma x1 comma x2 divided by x3 minus x0, where once again this gives you that, and this one is computed separately. Let's see, it'd be analogous to this kind of formula. It's a divided difference of second divided differences, but the labeling changes. It's going to be x2 comma x3 minus f of x1 comma x2, all divided by x3 minus x1. This will have more meaning, mechanically speaking, when we implement it in a spreadsheet, which I think is what we will do instead of doing it by hand. That pattern continues until you get to AN, which is an nth divided difference. And an analogous formula holds. I won't bother writing it down. And it does turn out that AN is going to be the coefficient of x to the n. These other a's, if you expand out this polynomial, are not necessarily the coefficients of the lower powers of x. Because the lower powers of x come up after a bunch of multiplications. But AN is the coefficient of x to the n, because the only way you get x to the n is with this last term, because you got n factors there. And you will get an AN times x to the n. This is also the coefficient of x to the n in the expanded form, sorry, of the polynomial. All right, it's going to be best to implement this in the spreadsheet. I was thinking maybe I'd have time to do it by hand, but I can see with 13 minutes left, we're not going to. So I'm going to chat. I was going to think about doing the sine function here, but let's change the example to the CDF of standard normal. And we're going to do, once again, a third degree polynomial approximation, not Taylor, but third degree, really Lagrange polynomial approximation. Change my nodes to 1, 1.282, 1.645. And 2.576, get rid of these other nodes. We're going to do through third divided differences. The X value, we're going to approximate the CDF once again is at 1.96. And what's the goal? Think about what we were just doing by hand. We're writing down formulas for these A's in this formula. We're really finding coefficients in this formula. The reason it's put in this form is because these formulas are very mechanical. Newton evidently was the first person to realize this, who actually implemented this 350 years ago for whatever scientific application he needed it for. So, meaning we're ultimately are going to plug in X into that formula. 1.96 is going to go into the formula. And moreover, since these A's, their formulas ultimately are divided differences where the first thing in the first spot is X0. These coefficients are only going to be in certain spots in the table. But we need to construct the entire table to calculate the correct coefficients. So again, just like with Neville's method, the 0th column you might say is the easiest to compute. It's just the data values. 0.841345. I'm just looking at these data values that I wrote down by hand up here. 0.900079. 0.95000015, 0.995002. It's only the first of these that's one of the coefficients. 0.841345 is A0. None of the other ones are coefficients, but I will need them to compute A1 and A2 and A3. Notice I'm putting spaces between these rows. It is more convenient, certainly with divided differences, to do that so that for the first DDs, you can put the numbers in the previous spaces, the rows that didn't have anything in them before. So for this first DD, this is actually easier than Neville's method. Do this minus this divided by this minus that. That is a divided difference. It's a first divided difference. It's a divided difference of 0th divided differences. A true difference quotient, if you like, or simple divided difference. That formula will get copied and pasted to these other open rows here and here. Again, these numbers are not going to be any of the A's, but I need them to compute the other A's. The A0 is in this one, the A1 is right there. Those are the coefficients. They're in the they're going to be in the diagonal from upper left to the middle right of this table I'm making. Are going to be A0, A1, A2, and A3. For this spot, it's a second divided difference. It's a divided difference of first divided differences. This is iterative. But divide by now, careful, x2 minus x0. Catch that? So for the second divided differences, so I'm using this formula right here now, and this will be the value of A2. I'm doing a divided difference of first divided differences and dividing by x2 minus x0. Copy and paste that formula down 2 spots. That's not any of the A's, but I needed to compute A3, the final A. will be this minus this divided by this minus that. I'm using this formula now. Notice I'm dividing by x3 minus x0. Actually, the really amazing thing about this, so you do notice my nodes are not equally spaced here. The really amazing thing about this is it works even if I rearrange the nodes to not be in numerical order. I do get different A's and a different form for this polynomial because I've rearranged the nodes and relabeled them. But you still get the same numerical approximation in the end. And in fact, you get the same expanded polynomial if you simplify it. Just amazing that it works. I'm not showing you algebra details because it's too messy. Okay, so there's the last coefficient. So A0 is 0.841345, A1 is this, 0.208, A2 is this, and A3 is this one. Now to approximate the CDF of the standard normal at x equals 1.96. Now I want to go back and think about this formula up here. I want to use that. A0 plus A1 times x minus x0. See what I did there? Plus A2 times x minus x0 times x minus x1 plus A3, we're almost done, times x minus x0, whoops. Times x minus x1 times x minus x2. And I never have to do an x minus x3 anywhere. Never in general have to do an x minus xn. It works. The algebra can be verified. So what should I get here? This should be close to 0.975. It should be, in fact, the same answer we got with Neville's method. Which was what? Where's Neville's method? I forgot. 0.9752242. Drum roll. Oh, sorry, I did it too quick. 0.9752241. Okay. Must have been calculator rounding that made it off a tiny bit at the end. And the error would be, the 0.97 thing we got with mathematics, 0.975002 minus this thing. That's small negative error. Again, the nodes don't have to be equally spaced, and they can even be rearranged to not be in order. Though it certainly makes more sense to put them in numerical order. It's nice, you might say, that it works even when they're not equally spaced, as in this example. On Thursday, we're going to continue in section 3.3 and talk about Newton's forward and backwards difference methods, which are essentially the same thing as the divided difference method here, but with different notation. And in that case, you do want equally spaced nodes in numerical order for it to work. It's a bit more easily programmable, especially in Mathematica for those. And it's going to involve the forward difference operator, as we talked about with Aiken's delta squared method, as well as something called the backwards difference operator. And I think it's kind of fun. We'll do a little bit of fun with forward and backward difference operators. Discrete calculus. We'll save the discrete calculus for Thursday. Okay. Which I do think will be a little bit of fun for you. Maybe this has not been fun, but I think that'll be a little bit of fun for you. I think it's fun. All right. Have a good day.